Okay, so thank you for the invitation, and also thanks, Anton, for the perfect introduction to my talk. So I will have to define Poisson manifolds. I'm very happy. I'm interested in Hamiltonian PDEs today, and so I'm interested in theoretical mechanics in general, and I think one main motivation for the Hamiltonian dynamics is that I think it's a very powerful way, and somehow yet not fully a good way of dealing with nonlinearities in conservative mechanics, and particularly in conservative PDEs, I think. I'm going to tell you a bit about some work I achieved during my PhD and some following of this. So a bit of Poisson geometry, the remainder of Poisson geometry first, and then symplectic groupoids, and third, a research project. Research project is about using Poisson geometry to construct numerical methods for Hamiltonian PDEs, and say the first two parts of this talk are one part of the research project. So let me give you some work I did. So it's based on 3 preprints. The first 2 preprints are more or less the 2 first parts of the talk. And the third preprint is more or less one beginning of the third part. So the first 2 are one way to deal with Hamiltonian dynamics and to approximate Hamiltonian dynamics on a Poisson manifold using symplectic groupoids. And the third one is the work about Poisson geometry and solid mechanics, and work about Hamiltonian PDE. I will tell you a bit in the third part. So, part 1. So I take a Poisson manifold, the way Anton defined it, and I will sometimes refer to the Poisson structure as Poisson bivector, so it's equivalent in general. We had several examples this morning. Let me give more examples. So I'm going to give 3 examples, and those 3 examples will follow us all along the talk. So you take M as a cotangent bundle, and the Poisson bracket coming from the canonical symplectic form. You can write everything in coordinates. So if I take Q coordinates on V and P, the associated cotangent coordinates, and then by vector become QHDP. The second example is the example of the dual of Lie algebras. So say here it's finite dimensional, everything is finite dimensional here. Is a canonical Poisson structure on G star. By doing so, identifying G star with G. The third example is quadratic, so I will make that precise in a moment. So this is somehow an example of degree 0. This is a linear example, and now I have a quadratic example. So let me put it in dimension 3 maybe, but you can replace 3 by n, and then with x coordinates on R3. This is also a Poisson bracket. If Aij is any antisymmetric matrix. And we're going to do some Hamiltonian dynamics on these Poisson manifolds. So thanks, Anton, again. I take a Hamiltonian, I mean a smooth function on M. Yes?
3 by n, do you get some condition on this matrix? Aij or still?
No. So yes, so it goes this way. So this is antisymmetric, and this you define like this.
Ah, okay. Because otherwise it's 0.
0.
Okay, and so one main feature of Hamiltonian dynamics on Poisson manifold is the underlying symplectic foliation I'm going to tell you about right now. That you also discussed. More notations. XH is the Hamiltonian flow, and phi H, the flow of H at time t. Say it's defined for all t. Doesn't matter for our talk. And theorem. And this theorem really matters for what we discussed right now. So the Poisson structure you put on M generate a singular symplectic foliation. Foliate M into singular symplectic foliation. So what does it mean? It means it induces a partition of M, and the leaf of M, I name f of x, is all the y such that y is reachable by Hamiltonian flows starting from x. Now we had 3 examples of Poisson manifolds here, and for all of them, the symplectic foliation is different. So this Poisson structure is said to be non-degenerate. It means for the symplectic foliation that, well, the symplectic foliation is trivial. For the Lie algebra case, it's provided by coadjoint orbits, and there you already see singularities of the symplectic foliation. So let me give you, so I start again with the example of spheres of Anton, right? Example of the example. Take SO3, you get that the leaves are spheres, right? If you identify SO3 with R3. And now, if you do Hamiltonian dynamics on that space, with colors, you start at a point X, and you do Hamiltonian dynamics on that space, and so by the very construction of, say, if you admit this theorem, your Hamiltonian dynamics will remain on the leaf. This every time. And now in mechanics, it turns out if you want to compute your Hamiltonian dynamic, your Hamiltonian system with a computer, if you choose a traditional numerical method like Runge-Kutta or the one you want, you will escape from the sphere. And in the long run, you will have undesired numerical effects that will completely mess up your numerical computation. So what really happens in practice is that, for instance, you converge to 0, and at some point, well, you stay here. So if you start at 0 with a computer, you will remain at 0 because your dynamics is trivial. But if you start a bit aside 0, well, you may converge to 0, and it's artificial, it's unphysical as an effect of the computation. So this is one motivation for constructing, like using, say, geometrical tools to construct better numerical schemes. And today, yes, it's true.
Because I know people from numerical analysis which tell me all the time, doing geometric numerics is no point. The machines are strong enough, you just do straightforward calculation of ODEs, and you get the right solutions.
No, this is
something the opposite.
This is something you can do in 5 minutes. So you take this Hamiltonian system with the Runge-Kutta method. So if you pick a Runge-Kutta method with a too high order, you won't see anything because it would take too much time to see the effect. If you take a small order and a very bad time step, you really see this. You really converge to 0.
Which is not too small, not too big the time step, and not too low the order. Will not stay on the sphere asymptotically?
No, you will not stay on the sphere.
Okay.
This is why geometric integrators were introduced.
Yes, I know that it's like this, but I know people from numerical mechanics, numerical analysis, which tell me the contrary.
But they are not interested in long terms, long times.
see the effect if you wait long enough.
Right.
Short effect, for short time you don't see.
We'll discuss with them.
So already at order 4, for instance, you need quite a long time to converge to 0. So also, it's a very easy system. So for this, of course, if you pick a really small time step and a really high order, you don't see anything. If the system is more complicated, for instance, Euler equation, I think it's really hard as an equation. And there, you need to know what you compute. Right? I claim if you don't use the Hamiltonian structure of the equation, you need some instability. Okay. About the symplectic foliation of the third one, it's a bit more complicated. So I can give you a Casimir, for instance, so for the third one, if you pick n equals 3 and this, when Casimir is you see it's singular, but so the regular leaves will be levels of this function. Well, x1, x3, x2. So you can draw this with your computer and see how the leaves look like. Right, so let me sum up three properties of Hamiltonian dynamics. The Hamiltonian is preserved. One thing I haven't said yet is that the Poisson tensor is also preserved, a consequence of the Jacobi relation Anton told you about. And the third property is that you stay on the leaf. So it's what this theorem tells you about. Now I'm going to tell you a bit about symplectic groupoids and how I used them to solve the question raised by this picture of the sphere. Okay, it makes sense actually to use local symplectic groupoids to do numerics for Poisson manifold. I'm going to tell you what this object is in a minute. But at first, say local symplectic groupoids are bigger objects that contain the Poisson manifold. They are of dimension 2 times the dimension of the Poisson manifold. And one interpretation of local symplectic groupoids is that the space that desingularize the symplectic foliation in some sense. And we've seen that the singularity at 0 of this symplectic foliation brings problems for numerics. So it makes sense to try to desingularize the geometric space you want to compute on to look for better results. So let me write the definition. So a B realization is, for those, I know some of you know Poisson geometry, so B realization are related to local symplectic groupoids. B realization are just a tool to do computation on local symplectic groupoids. I'm going to tell you what this is. It's a tubular neighborhood of the cotangent bundle of M. A tubular neighborhood of the zero section. And then two submersions from U to M, such that the restriction of alpha and beta to the zero section are the identity. On M. And you ask alpha and beta to be Poisson and anti-Poisson. So you have a notion of Poisson morphisms that it's actually the same as the Lie algebra morphism. It's just about commuting with the bracket. And on T star M, you have a Poisson bracket. You have a Poisson bracket on T star M, and you have a Poisson bracket on M. So you can ask alpha and beta to be Poisson morphism. And anti-morphism is just a morphism with a minus. Alpha Poisson. You ask alpha and beta to have symplectic orthogonal fibers. It's just a geometrical assumption. Means this actually. So let's make a picture of my bigger space. So I have M here that I identify with the zero section. I have T star M, my tubular neighborhood, U, and if I have a point on T star M, I have two ways of projecting it by alpha and beta. And now I have Hamiltonian dynamics on the base, looking at ITH. And what I did was to lift up this Hamiltonian dynamics in this bigger space.
Symplectic groupoid integrating your thing, then this is, you just apply the tubular neighborhood theorem near the identity and you get this.
Yeah, it's Weinstein tubular neighborhood. Okay. Because the zero section is Lagrangian, as well as the identity section in maybe a proposition that it exists, just as you said. And now, let me explain how I related phi th and the local symplectic groupoid. So the idea is to describe Hamiltonian dynamics by using some submanifolds of the tubular neighborhood U. And those submanifolds are described by generating functions. It's the idea of Hamilton-Jacobi theory. at least from a geometric point of view. So it goes like this. So I give you one direction, but it's actually, you can make it into an equivalence. Write it like this. So this equation will tell you a condition on ST so that the graph of dST in U will recover the Hamiltonian flow. So then by setting LT what you can prove that for small t, alpha, since alpha has transverse fibers to the zero section, you can inverse alpha if you restrict it to LT. And you recover the flow of H by inverting alpha and projecting again by beta. So in practice, you will have your LT like this. For t equals 0, it's just the zero section. And for small t, it's a perturbation of the zero section in t star m. And then phi th is recovered by alpha, by inverting alpha restricted to LT and projecting again by beta. The upshot is that, so this is as hard to, yes?
What the dst upper star means?
Yes.
Alpha star of H is a function on t star m roughly, and then
right. And dst is seen as a map from M to T star M.
Ah, I see. Okay. Yeah.
Okay. How much time do I have left? I have 20 minutes again. Okay. What was I speaking about? Completely forgot. Ah, yes. So yes.
Question related to the previous question. So, like, do you mean like in the left-handed side of this stuff, like you have a time derivative of a function, right?
I didn't understand.
In the left-handed side of this system, you have a time derivative of a function, right?
Yes. So you can see.
Yes. Ah, yes, please.
You can see it pointwise if you want.
And on the other hand, the right-handed side, you have a function h pulled back by alpha and then pulled back by dst, right?
Right. If you write it this way, so this is a partial differential equation. If you write it this way, if you fix x, so you don't have to go into time derivative of smooth function. It's just pointwise.
My point is, like, I think h is a function which is a zero form, right?
Sorry again.
I think h is a function, right?
H is a function.
So this is a zero form. So you are putting back this zero form by alpha.
Yes. There is, yes.
And alpha is again a map, right?
Yes.
And the dst is a map from M to T star n.
T is a map from M to T star M, yes. So you have, it's an equality of maps from M to R at the end.
Oh, okay, and then it's a map in.
Yes.
Oh, okay.
Okay.
I think, yeah.
And so what I wanted to say, so yes, so this equation is as hard to solve as the Hamiltonian dynamics on M. So that's it. But here, the thing is, you can truncate, you can solve this equation up to some order. Okay, an order k, and then you can approximate this manifold LT by some LTK for big K, K being the order of your approximation. And then here you don't get phi th anymore. But if I set K here, you will get phi th plus a small o of tk. And in addition, if I write phi t equal beta I write phi t as the diffeomorphism induced by the submanifold LTK. This is again, so it verifies again the properties I listed on the blackboard. So it's again a Poisson diffeomorphism. Again, it stays on a leaf, and in addition, well, it does not preserve H anymore, but it oscillates around levels of H. From a numerical perspective, it's really efficient and really powerful as a result. And the reason is this phi t is the flow of Hamiltonian being close to H. So it's a flow of Hamiltonian HK, say, which A minus HK being of order K. Right. So let me tell you about my about what I do right now to use this result. Yes.
So you have this method of approximate integration, which you says oscillates because it's Hamiltonian, but when you actually do it on a computer, you have like a floating point error, right? Wouldn't that be a problem eventually?
Right, but so that error is really small compared to the error you make by actually approximating the dynamical system. So it's not that one that you want to care about first.
But this result that it will actually oscillate, this will be true if we did the calculation with symbolic arithmetic, right? Then that would be true. But if we do a floating point calculation, then it's not quite true.
Okay.
No, I'm just asking. I don't know.
So I claim anyway that the order the error you mentioned exists, yes, but it's really small compared to this.
Just a remark to this numerics. Clifford Truesdell I read 2 books of his. I mean, he was the founder of the Archive of Rational Mechanics, which was a journal which for a time accepted scientific papers in Latin. And he wrote 2 books. One was An Idiot's Fugitive Essays on Science, and the second was The Strange History of Thermodynamics in the 19th Century. And in one of these books, I think in the first one, he said, if in Euler's time they would have invented computers, mankind would never have reached the moon, because then they would not have searched for things like conservation of energy and angular momentum, and then each computation that they did to compute the orbits to reach the moon would have exploded in short time. So that is maybe.
But the orbit of Earth would also explode, so they would know that something is wrong.
Okay. Okay, thank you. So there are several things you can do with this. So first, since the space of such submanifolds being the graph of exact or closed one forms in the symplectic groupoids are of importance. We're about to publish an algebraic formalism to recover the Taylor expansions you get by developing this. So for those who know, there is a Postly algebra describing finite order solutions of Hamilton-Jacobi equation. This is joint work with Adrien Laurent. Second work is actually about what I told you at the beginning, and it goes like this. So you start with a Hamiltonian PDE, the Euler equation, and you would like to use this to construct a robust numerical method for the Euler equation. And the problem is here, actually. So if you invert a smooth map in the finite dimensional setting, it's just looking at a fixed point, not so hard from a numerical perspective. If you go infinite dimensional, you need to inverse differential operators, and it's much harder. So the idea we have is to project the Hamiltonian PDE into a finite dimensional setting and then to apply this. This exists already in some very particular cases. I can mention something called Zeitlin model. So this is for Euler equation on the sphere, on the two-dimensional sphere. In general, it's not known how to do that, but I have plenty of ideas we can discuss. Also, one print I mentioned, so the third one here is about constructing a Hamiltonian formalism for a Hamiltonian PDE of solid mechanics, which is called Timoshenko model. Turns out, in that solid mechanics setting, the Hamiltonian formalism seems to be a way to deal with high frequencies instabilities. And so constructing a Hamiltonian method for this would be a very nice way to deal with instability in solid mechanics. It's something I do right now with, so the preprint is with Loïc Lemarec. Right. But in general, the direction is to try to extend this result to the infinite dimensional setting to deal with instabilities in mechanics. So yeah, I'm done here.